So good morning children. This is 11th Physics Unit 7 Properties of Bulk Matter, Chapter 9 Mechanical Properties of Solid. This is your second video. So today we are going to start with Hooke's law. So children, we have already learned about stress and strain. So here the scientist Hooke, he gave us the relation between the stress and strain. So for that he performed an activity, he performed an experiment, as you can see in the screen. So here children, AB is a metallic spring which is supported on a rigid support, right? And you can see that with the metallic string at the bottom, you can see a pan is attached, and on the pan we are going to put the known weights, right? Now here we are having a scale which is fixed, right? And the wire AB at the lower end is fixed with a pointer P, and this pointer P can slide over the scale, right? It can slide over this vertical linear scale. Now what we are going to do is we are going to put some weight in the pan. We are going to put some weight in the pan. We are going to record the reading of the pointer on the scale. Fine. And we will go on adding the weight, and we will go on noting down the extension in the spring on adding the weight in the pan, right? And after finding out the extension and the weight, we will calculate the stress and strain. And then when we plot the graph of extension versus the load we had applied, the extension in the length of the wire and the load, the weight that we had put in the pan, you will see that it is a straight line graph showing that as we increase the load, that is, as we go on putting the weight in the pan, the extension in the wire goes on increasing. That is, with the increase in the stress, the strain goes on increasing. So, stress and strain, they are directly proportional to each other. This is the statement of Hooke's law. So, Hooke's law says that the extension that is produced in the wire is directly proportional to the load applied. There is an exception here, that is within the elastic limit. Within the elastic limit, because after the elastic limit, the stress won't be directly proportional to strain. That we are going to see what will happen after the elastic limit, just after this topic, right? So according to Hooke's law, children, the stress is directly proportional to the strain within the elastic limit, and if we remove the proportionality sign here, and constant will appear, and this constant is known as the modulus of elasticity. It is known as the modulus of elasticity. Right, children? The modulus of elasticity, which is denoted by the symbol E. We will learn this in detail. Now, let's see the curve of stress versus strain. Let's see the curve of stress versus strain. So, this is exactly the curve in your NCERT. So, children, here you can see on the y-axis we are having the strain, and on the x-axis, on the y-axis we are having the stress, and on the x-axis we are having the strain. So, this is again the same experiment, that is on a rigid support we are fixing a wire, and at the bottom of the wire we have fixed a pan in which we are going to place some known weights, and we are going to note the reading of extension on the wire, and then we are going to calculate the corresponding stress and strain. And after calculating the stress and strain, we have plot the graph. So this is the graph for stress versus strain, and the nature of graph was found as shown on the screen. Right, now let's start with the explanation of this stress strain graph. Right, here we had used a wire and we had put the weight in the wire, so the wire is going to extend longitudinally. Right, the length of the wire is going to increase, so the type of stress which we had done over here, as the length is increasing, it will be the tensile stress. So this is your graph for the tensile stress. Right, children, now let's understand each region of this graph. Now, initially, as you can see, this is your region OA. So OA, as you can see, it is a straight line graph. Means here the stress is proportional to strain. Means it obeys Hooke's law. So your point A is known as the point of proportional limit. It is known as the proportional limit. So OA is a straight line graph where stress is proportional to strain, and so Hooke's law is obeyed in the region that is OA, and point A is your proportional limit. Right, now further children, when you increase the stress, how you are increasing the stress? You are putting weights, right? First, suppose you had put the weight of 10 grams. Now you are putting 10 more, 10 more. So you are increasing the weight, right? You are increasing the load. So stress will increase, right? So now further you will increase the stress from point A. So when you increase the strength from point A, the strain also increases. That is, the strain reaches point, that is AB. So here you can see that AB is not a straight line, right? As AB is not a straight line, the stress is not proportional to strain. And so in this region, that is region AB, Hooke's law is not obeyed. But if we remove the stress, means if we remove this load, children, then the wire, it will retrace its path from B to A to O, and it will regain its original shape and size. Similar is with OA. If from point A, means after putting, suppose you had put a weight of 10 grams and it reached from O to A, and suppose you remove that weight 10 gram, then it will come back from A to O, that is, it will again regain its original shape and size. That is, the same is at point B also. Till point B, if you remove the stress, then it will regain its original shape and size by retracing its path. Now, further from point B, if you increase the stress, that is from B to C. Now children, here you can see that you have increased the stress so small, means the weight that you are putting, suppose it is of only 1 gram, means you are putting 1 gram, and see the increase in the strain, see the change in the length of the wire, so large change, right? So from point B to C, even if you are putting stress very less, you are putting 1 gram, but the increase in the strain, the extension in the wire is large, right? And if from point C, if you remove the strain, if you remove the load, if you remove the weight, then it will not regain its original shape and size, but it will it will cover or it will follow, it won't follow C to B, B to A and O. It will follow the path that is CO dash, right? So the wire has permanently got set in this parameters, in this configuration. The wire will never be able to regain its shape. So this strain, this elongation in the wire will remain there forever. So the wire is said to be permanent set, and this deformation is called plastic deformation. Okay, children, this is your plastic deformation. Now, let's move further. Now, further is from point C to D. From point C to D. So, children, from point C to D, you can see that if you increase the stress, the strain will also increase, but it is not linear, right? But from point D is known as the tensile strength. Means this is the point where it has reached its limit. And further, if even if you remove the stress, even if you remove the load, the wire is going to break. Right? So the tensile strength is the maximum the maximum load it can withstand. And after this D point, it is going to follow the curve that is DE. Even if you remove the strain, it will be strained. Even if you remove the stress, it will be strained. So it is going to flow down. Right, children? So now let me show you NCERT over here. So children, even if the load is removed, say at any point between B to D, at any point between B to D, the body will not regain its original shape and size. And here, in this case, even if you make the stress zero, even if you remove the load entirely zero, but the strain will not be zero. It will have some strain. And so the material is said to be permanent set. And this deformation is called the plastic deformation. Right, children? Further, they are explaining you the point D. That point D is the tensile strength, right, beta? So beyond this, if you increase the strain or even if you reduce it, then what will happen? The breaking point, the breaking stress will be reached and the substance will break. So this is your stress strain curve. Now children, your modulus of elasticity, we saw in the Hooke's law that stress is proportional to strain, and on removing the proportional sign, we got a constant there, and that constant we had named it as the modulus of elasticity, which was shown with the alphabet, that is E. So this modulus of elasticity, it is the property of the material, right? And depending upon the strain, what type of strain you are putting, what type of stress you are putting, this modulus of elasticity, they are of three types. The modulus of elasticity is of three types. Firstly, the modulus of elasticity, as we know, it is stress was proportional to strain. Remove the proportional sign, the constant is E, and that is your modulus of elasticity. So if you want to make modulus of elasticity as subject of formula, this strain will come here, and your modulus of elasticity can be defined as stress upon strain. This modulus of elasticity is of three types. Let's talk about the first modulus of elasticity, that is your Young's modulus. Young's modulus. So children, Young's modulus is denoted by the symbol Y. Young's modulus is denoted by the symbol Y. So Young's modulus is equal to normal stress, means you are applying the deforming forces that are normal to the area, right? And the strain that is produced is along its length, is only in, there is change in its length because of the deforming force. So the strain type is longitudinal strain. So your Young's modulus is defined as the ratio of normal stress to longitudinal strain. And as we know, children, that strain, it does not have any unit, but stress, it has unit, that is Pascal. So the SI unit of the Young's modulus, that is Y, is Newton per meter square, that is Pascal. So Young's modulus unit is Pascal. Right, children? So Young's modulus, its value differ from material to material. Young's modulus depends upon the nature of the material, and it does not depend upon the dimensions. It does not depend upon length of the substance, breadth of the substance, area of the substance. No. Right, children? So this is your Young's modulus. Let's talk about the second type of modulus of elasticity, and that is your bulk modulus, which is denoted by the symbol B. Your bulk modulus, which is denoted by the symbol B. So bulk modulus, children, as the name says, here the strain that is involved is volumetric strain, right? Bulk modulus, as we see, it is denoted by the symbol B. So your B equals to normal stress. Stress to normal rahega, right? It is acting normally only. But the strain is volumetric strain, means because of the stress, there is change in the volume of the substance. So your bulk modulus is defined as the ratio of normal stress to the volumetric stress. This is all within elastic limit, right? Volumetric strain is change in volume upon original volume, right, beta? And normal stress is what? Force upon area. So we can write, instead of force upon area, pressure. So your B equals to P upon del V upon V. Again, the unit of bulk modulus B is pressure, because volumetric strain does not have any unit, right? And here one more important thing they are showing us about the sign. What does negative sign means? Negative sign means its volume is decreasing. And if the sign is positive, if the P is increasing, and if the sign is negative, it means the positive, then the volume is increasing, right? This is the second type of modulus of elasticity. Let's talk about the third type of modulus of elasticity, which is known as the shear modulus of elasticity or modulus of rigidity, or it is called, children, modulus of rigidity, and it is denoted by the symbol, and that is, it is denoted by the symbol, and that is G. Okay, beta. So shear modulus is the third type of modulus of elasticity, and it is denoted by the symbol G. And here, children, we are not going to have the normal stress. No, here we are applying the stress tangentially, right? We are just deforming, we are just changing its shape without changing its volume, right? So it is tangential stress upon tangential strain, or you can call it as shearing stress upon shearing strain, right? So this is it. This is your third type of shear modulus, and its unit is same, and it is denoted by the symbol that is G, and the symbol for stress is sigma, and the symbol for the strain is theta. So it is sigma by theta. This is your shear modulus. So as you are applying the force like this, So it is getting deformed. The shape is changing. There is no change in volume. So this is your shear modulus. Right, children? Next, what we are going to do is, next we are going to determine the Young's modulus for a material. So how to determine the value of Young's modulus? So children, for that we require an experimental setup which is shown to you in the diagram on the screen, right beta? So here what you are having, here you are having A and B are two long straight wires. They are of equal length. Their length is equal, their area of cross section is equal, and they are made up of the same material. If one is made up of copper, the other one will also be made up of copper. Now both of them, you are suspending it from a rigid support. Now here your wire A is your reference wire and wire B is the experimental wire. So you are going to perform your experiment on wire B. You are going to keep, here you can see some pans are attached, and in this pan we are going to put some known weights. Right. So we are going to perform our experiment on experimental wire B, and for readings we are going to refer to wire A, and so it is known as the reference wire. Right, children? So here at the end of the wire B, a pointer is attached which can slide over the vertical scale on the reference wire. Right? Now what you're doing, now how you're going to start your experiments, you are going to put some weight on both the pans. Why on both the pans? Because beta, if some kink, some fold, some turn is there on either of the wires, it will be removed and both the wires will become straight and parallel. Right, now we are going to note the reading of the main scale. We are going to note the reading of the main scale and the vernier scale. Now we are going to put in the experimental wires pan, we are going to put some known weights. So as we put the known weights, there will be extension in the wire B and the pointer will slide over the vertical scale and it will show us reading number 2. So we will note that reading, right? There will be elongation in the wire. There will be change in the wire. So we will note that reading, and the difference of the two reading will give us del L. The difference in the two reading will give us del L. Right, beta? L we know, length of the wire we know. Mass, the mass which we are putting it in the pan, that we know. G value is known. Area of the wire, pi r square, is known. So all the things are known now. Why we did experiment? So that we can find the value of elongation. That by putting this much weight, the elongation is how much. So for this we did the experiment, we got the value, and then we will calculate the value of Young's modulus by putting these parameters in the formula y equals to mg into L upon pi r square into del L. So children, with this, the chapter 9 mechanical properties of solid is completed. Thank you, Vita.